All right, so now we're going to look at the binomial distribution. And this is what happens when you have two choices. Usually we call them a success and a failure. So flipping a coin is an example of that. Because if you want heads, that would be a success. Not getting heads would be a fail. A multiple choice test is an example of that. Because you either get the question right or you get it wrong. And your probability changes because now there's 4 choices, or depending on if it's one of those crazy bio ones where you have like 8 choices. Have you ever had those? Multiple choice where it's like you got A, B, C, and D, and then the next one's like A and C, A and B only, none of the above, all of the above, and just like by the day you're like, oh, I know it's A, but it might be C as well, and then you just get it wrong. Anyways. So this binomial distribution, and it's also known as Bernoulli trials, and you got a success and a failure, and you usually have your probability of success shown by the letter P and probability of failure shown by the letter Q, and those two together add up to 100%. So they'll always add up to 1. So what you do is you do a fixed number of trials. So let's say you're flipping a coin. You say, I want to flip a coin 10 times. What is the chances that I get 3 heads? What are my chances of getting 4 heads, 5 heads, 6 heads, 7 heads? All of those. Right? Each of those trials, there's only the 2 possible outcomes. They're all identical, and they're all independent. Just like flipping a coin, it doesn't matter what you flipped last time. It's not going to affect what's going to happen next time. The coin's not going to try harder to be tails the next time because it wasn't tails the time before. Or even though it's 50%, since you got heads the first time, that doesn't mean, oh, you're guaranteed to get tails the next time to make sure it's 50%. So all of your probabilities are the same each time. Probability of success is the same, and probability of failure is the same. So an interesting thing happens as a result. We get this wonderful formula. And you've seen it before. Do you know where you've seen it before? No, that's okay. Because the notation's a little bit different. Oh, you do see it, yes. It is, like last year we sort of had the tk plus 1 equals n choose k, a to the n minus k, b to the k, right? And that was for a binomial expansion. Well, what are we doing now? We're doing a binomial distribution. So this was for when you had a plus b to the n, right? Now in IB notation, the n choose k is written, and instead of using k, they use r. In that format, n choose r that way. And you were shown that last year, but generally we use the n choose k. The IB course more often puts it in these brackets with an n and an r. Not to be confused with the vector notation of the transformation you had in one of your labs, right? With the p and the q, and the p was the x and the q was the y. We haven't learned the vector notation yet, but we will learn that later on. So it has that same format, and the reason we have that in n number of trials, okay, and you want to find out what are your chances of getting 5 heads, so you would have r as 5, your probability of success happening 5 times, and your failure happening 3 times. Okay, you want a quick example to see why this happens? Let's say you flip a coin 3 times. If you draw a tree diagram, heads, tails, heads, tails, heads, tails. Okay, so we flipped a coin 3 times. Now, if you were saying, what are your chances of getting heads twice? Well, someone might say, well, maybe we shouldn't use heads and tails. let's say you're guessing on a multiple choice test. We can still use the same thing. We'll use T that you got it right for true and H for horribly wrong. Okay? So your chances of getting it right, we'll assume it's a 4-choice test, and horribly wrong would be 3 out of 4. So we could add all of these probabilities along the way. It's just nice to use a multiple choice one because if you use heads and tails, they're all halves, so it's hard to see that the numbers are changing. And this is horribly wrong, and this is true. So what happens, you want to say, what are my chances if I guessed on my 3-question multiple choice test? What are my chances that I get exactly 2 right? Well, you might start to think, I want to get 2 right, so that will be, I've got a 1 out of 4 chance, a 1 out of 4 chance, and a 3 out of 4 chance because I need to get 1 wrong. But that's only one case. Can you see that that's only the one branch of getting true, true, and then horribly wrong? There's other cases. How many cases are there? Well, we need to, so notice here, in this case, we want to get 2 right. So our R would be 2. We have 3 trials, so our N would be 3. This first part, the N choose, the 3 choose 2, which is equal to 3, is how many branches have that? Okay? So the first part of our formula, 3 choose 2, which is equal to 3, tells us there's going to be 3 branches that have 2 true. We have that one here. Whoa. We got to be a little bit more bendy. Ooh. There we go. The program automatically draws straight lines if it thinks you want to draw straight lines. We have this branch here, and we would have had 2 true if we would have went this way. So there's 3 branches, and the 3 choose 2 does that for us. That's why it comes out at the beginning. Then no matter which of the branches you choose, since the probabilities stay the same and each trial is identical, we'll have 2 1/4 and 1 3/4. So we have our 1/4 squared, and that matches up your probability of success to the R. And you have 3/4 once, which matches up with 1 minus P or Q to 3 minus 2, which is whichever ones are left. Okay? The nice thing about this formula is you can figure out complicated questions, like if you toss a coin 50 times, what are your chances of getting 25 heads? You can plug it into the formula and it will figure it out for you. We have nice ugly notation for this, so you have to get used to stuff like this. So the probability function, random variable x, it's binomial, that's what the B stands for. We have 6 trials, and the probability of success is 40%, or 0.4. So if we wanted to calculate it, we could plug it into our formula. And here we've got our probability distribution, the probability that x equals r. So 6 choose r, 0.4 to the r, and then probability of failure would be 0.6, 1 minus 0.4, 6 minus r. And if you wanted to find a specific one, so here's our example. If they tell us that it's a binomial distribution with 5 trials and the probability of success is 60%, what are your chances of getting exactly 4 right when you do that experiment? So this is the hard part, understanding what the heck are they asking us, right? So here, You recognize this part as a probability distribution. Remember when we did those with our charts? 0, 1, 2, 3, 4, 5. Does it make sense that if you had 5 trials, you could get none of them right, up to 5 of them right? We're looking for this number right here. We're looking for what's the probability that x equals 4 if you had a 60% chance of getting it right each time. So we plug it into our formula, and we find out that that number would be about 26% or 25.9%. Now the formula is not hard, but it is a little cumbersome because you've got to go to the probability part of your calculator to do 5 choose 4, unless you know that by heart. So mental math-wise, you might want to re-look at your combinations formula and say 5 choose 4. Maybe you remember 5 choose 4 is equal to 5 choose 1. And if you have 5 items and you want to choose 1, how many ways can you do that? 5 ways. But you still, 0.6 to the power 4 is usually something that's not very good for mental math. So you've got to go to your calculator for that. You've got to go to your calculator for the 0.4 to the 1. I hope you don't need to go to your calculator for that one. But then multiplying it all out, you'll need to go to your calculator for that. So wouldn't it be nice if our calculator had something built in that did this for us? Oh, it does. So we're going to find the binomial distribution. Number of trials, probability of success. So let's see if we can find that. So we go to second button, go to vars, because above it says distr, which stands for distribution. Okay. If you were worried that that maybe stood for destroy and you never wanted to touch that button in case it was self-destruct, it stands for distribution and it is safe to use. And you have to keep going down until you find it. So this is one of those ones where if you forget where it is on the exam and you're searching and searching and searching, you won't find it because it's never on the first page. So we want to put in the number of trials and the probability of success. So if we do 5, 0.6, which was our last one, what's going to happen is it's going to give us all of our answers. It's going to give us our complete distribution, probability distribution chart. What I like to do with this answer is I like to store it often into list 2. Because then if I go to my stats button and I go to edit my lists, I've got it in list 2. And in list 1, I'm just going to clear my list 1. I can put 0, 1, 2, 3, 4, 5. And then I've got my probability distribution chart stored in my stat list. And you can go right here and notice in number 4, there's our 25.9%. So if we have a probability of success of 60%, well, then we can find out what are your chances of getting all 5 of them right? Only 8%. You got a 34% chance of getting 3 out of the 5 right. Now another thing we can do with this binomial PDF, so if I go back to distribution, I think it was the letter A, wasn't it? Ooh, cool. This time it came up like that. Did yours come up like this? Okay. So number of trials, what do we have? We had 5 trials, probability of success 0.6. Now, this is optional to put the x value in. You can leave it blank, then it will give you all of them. If you put in a number, then it will just give you that. And the paste option, there it pastes it back into here, and then it types it for you. I wonder why I didn't go to that the first time I hit it. The first time I selected it by going this way. So if you leave this one blank, then it gives you all of them. So just for fun, let's flip a coin how many times? How many times should we flip a coin? Twice. We won't get too crazy so far. Our probability of success is 0.5. Okay? So let's paste that, and we see that your chances of getting no heads is 25%, one head is 50%, and two heads is 25%. Makes sense. We've seen this before. Okay? Now the question is, well, if I flip a coin twice, getting 1 out of 2 heads is what the average should be, and it comes out to 50%, which is what I was flipping to begin with. So now my question is, if I flip a coin 8 times, should I get heads 4 times? Should that be 50%? Because it was 50% here for 1 time. So we're going to go back to that, just test that out. You can play around with. So I'm now going to move it up to 8 trials. I could find out specifically, what are my chances of getting 4? Is it still 50%? No. It's quite a bit less. 27% chance. If you flip a coin, the more times you flip the coin, yes, on average you still should get 50% heads, but the more times you flip it, the more options you have. So it reduces all of those, because that probability has to get distributed all the way out. So this answers your question before of you're flipping a coin 100 times. All right. So play around with that. If you want to see all the probabilities, you don't put this last number in, or you leave the x value blank. But then in order to see them nicely, I like to store them into a list. And usually I store them into list 2, so I can fill my list 1 with the 0, 1, 2, 3, 4, 5, 6, and so on. Okay, so let's do an example that deals with that. Manufacturer finds that 30% of items produced from one of the assembly lines are defective. That's not very good. 30%. I think they should get a new factory. So this is where this is really useful for a company, because they know what kind of, they've got data on what kind of percentages are defective, and then they ship something out, and they can tell their customer, you know, we've been having some problems. You should expect to see about this many that are defective in there. Hopefully you're not at 30%. Yeah, you could get a whole batch, that's bad. But anyway, so they take 6 out, and we want to find the probability that 2 are defective. So what we're trying to find here, what is our probability that 1 is defective? Our p-value is 30%. And we've had 6 trials. So we can either go to our calculator or we can use our formula. With our formula, we'd have 6 choose 2. Probability of success is 0.3 to the power 2. Probability of failure, which is not defective in this case, is 0.7, and that would happen 4 times. someone type this into their calculator, someone else go to the formula. We have 6 trials. 0.3 are defective. What is the probability of getting 2 of them defective? And barring any crazy mistakes, did you get 32% with both methods? 32.4? Now in part B here, they say at least 2 are defective. So we could do cases. We could do this formula, 6 choose 2, because that would be 2 defective. Then we could figure out 6 choose 3, because that would be 3 defective. Then 6 choose 4, 6 choose 5, and 6 choose 6. There would be 5 different cases. You could find them all out individually with that formula and add them all up. Can you see that you would have a lot of decimals to work with, and it might be a little bit messy, and you might lose a rounding error because you forget a decimal, or just the chances of making a mistake are not very, are problematic, are easy to do. Okay? With at least 2 defective, which ones are you not counting? You're not counting none defective and 1 defective. So another way of doing this is 1 minus the probability that there are none defective and minus the probability that only 1 was defective. So this would be less work, but you would still have 2 calculations to make using your formula to figure it out, right? Because this would be 1 minus, and this would be 6 choose 0, 0.3 to the 0, and 0.7 to the 6. And then you'd also minus 6 choose 1, 0.3 to the 1, and 0.7 to the 5. Of course, you could get those values from your calculator, and if you didn't put specific values into your calculator, you would have all those distributions in list 2, and those numbers would be easy to see. So if I go to my calculator again, and instead of putting the 2 in here, I just have 6 and 0.3. That'll give me all of those values. And if I would like, I can store those into list 2. Now when I go to my stat button and edit, I've got that data in list 2. And I've got the fact that 0 is 11%. One of them is 30%, so I would have to do 1 minus that 11% minus that 30%. And get roughly around 59%. Now, wouldn't it be nice if there was something on your calculator that did this quicker? Well, there is. On your calculator, there's a binomial PDF. That's your probability distribution. And a binomial CDF. The C stands for cumulative. We've done cumulative frequency charts, right, where you're adding things as you go. There's also, for binomial distributions, a cumulative one that adds things up as you go. So we're going to take this exact same information that we had before. Last time we did binomial PDF and stored it into list 2. Now I'm going to go to distribution, and you'll notice that right under binomial PDF is binomial CDF. Push enter on that one. We still have 6 trials. Our probability of a defective one is 0.3. We can find out a specific value. So if we wanted to add up 0 and 1, then we would find out the probability that x would be 1. If we would like to add 0, 1, and 2, then we would put x as 2. If we leave it blank, it calculates them all. I'm going to leave it blank right now. I'm going to calculate all of them. And I'm going to store this into list 3, just so we can pair our list 2 to our list 3. Okay? So now if I go to my stats and I go to my lists, does it make sense that the first ones would be the same because you're adding them up. You've only got one thing. It's going to be the same. My second one, my 42%, can you see that that's my 11% plus my 30%? And with the decimals, it comes out to 42%. And then if I did the 42% plus the 32% next, I'd get 74%. And once you've added them all up, you should get 100% as the very last one. So we've got our data here as well. So we could have solved this previous question, and the work that you could have shown is 1 minus binomial CDF of 6 trials, 0.3 probability of success, and we wanted to have the cumulative one up to 1, because what would be left is 2 through 6. So if at least 2 are defective, our cumulative probability would count up to 1. And you'd put enter on that, and you would get your answer. Let's just get our answer. 1 minus binomial CDF. This time, we're wanting to go up to 1. Oh, and I didn't do it in where I wanted to. Well, we'll just put our answer in list 1 right there. Perfect. 0.580. This is a nice one for 3 sig figs because when you round it, it was 0.5798. When you round it, you'd get 5.8. You have to include that extra 0, so you have your 3 sig figs. And that's your probability at least 2 are defective. So, there's another example here for you. Try that one. See if you're able to get it. And then this one here at the bottom is just the one that we just did. And you could show the probability that you're trying to find by saying at least 2, then the probability of x is greater than or equal to 2. Oh, you type this into your calculator. You had 3 trials, 50% chance. What's the probability that you would get 0, 1, or 2? And what number did you guys get? To 3 sig figs. Yep, binom CDF 3.5, comma 2. 8.75. 0.875? Awesome. Any others get that same result? Excellent. So now this is where this next example I'm going to get you to try. Sophie has 10 pots. You got a probability of germination. So you can figure out what's the probability. All the seeds will germinate. What are the chances of that? What are the chances 3 seeds will not germinate? So try this one. I'll put up the answer in a second. I'll put up the answer to A here so that you can see if you're on the right track, either with the calculator or with the formula. So that only 3 seeds will germinate? Well, if you're using the 0.8 for success, which is probability of success, 3 seeds not germinating would mean 7 seeds would germinate. Did anybody use the 3, but now said, I want to consider success when they don't germinate, because you could fill it out this way as well. 20% that they won't germinate, I want to find 3 of them. So 20% chance that you'll get 7 plants. Probability that more than 8 seeds do germinate, well, you'd have to either find the probability of x equals 9 and the probability of x equals 10. You could use your formula to do that. There's only 2 cases. Or you could do 1 minus binomial CDF all the way up to 8, because then that would leave 9 and 10 left. One of the things that I find about these questions is when you come across them on a test or an exam, they kind of, no matter how many times, like I've done them a lot, and you haven't done them a lot, but they still, when you come across them on an exam, they sort of catch you off guard. You're sort of like, whoa, what kind of question is this? So some hints that I've found in the past for like, how do I know this is one of these binomial distribution questions? They give you some sort of probability, and they tell you that something is happening a certain amount of times. Okay, because you need a number of trials. So those are things I'm looking for. 10 pots, and then they tell you the probability of each thing individually. And there's a probability of success and a probability of failure. So to be able to recognize those things and then say to yourself, oh, this is a binomial distribution, okay, then you can go either to your formula or to your calculator. Now your calculator is easier if you know how to use it, but if you forget where the buttons are, that's not going to be very helpful on a test. So either you have to make sure you know where to find those buttons and use them. The nice thing about the formula is it is on your formula sheet, so it's not something that needs to be memorized because it's there, and you've already seen that formula before when we did permutations and combinations. So there's a homework assignment there for you to practice some.